We constantly guess what the future will look like, but we rarely ask how it will be funded. Let's run the numbers. Specifically, we examine the economics of fully autonomous factory automation. If human labor is completely eliminated from the production line, we might expect manufacturing efficiency to rise indefinitely. However, this assumption ignores the structural constraints of classical specialization theory. Under this assumption, machines execute tasks with perfect precision, but they do not automatically capture unlimited efficiency gains. Diminishing marginal returns eventually constrain the division of automated tasks. This mismatch creates an unexpected economic bottleneck. When human labor costs fall to zero, the physical and software coordination overhead of specialized machines becomes the new binding constraint. We must analyze how incentives shift when the coordinating unit is a machine rather than a human. The removal of workers does not eliminate trade-offs, it merely relocates them. So, does a factory with zero workers escape the limits of productivity growth? The answer lies in the division of labor ceiling, where coordination costs overtake specialization gains eventually. As autonomous factories attempt to subdivide production steps, we observe the binding scarcity. The bottleneck shifts from worker training speed to the transaction costs of machine task switching. When human wages disappear, the incentive to specialize machinery increases. However, the physical retooling downtime and data bus latency remain highly scarce and costly to manage over time. Here is the constraint: we cannot divide physical tasks infinitely without introducing mechanical friction. The scarcity of coordination bandwidth sets a hard limit on the actual factory throughput. The observable consequence is a sudden stagnation in capital productivity. While labor costs drop to zero, the capital expenditure required to synchronize specialized machinery rises to historic levels worldwide. It comes down to scarcity. Automation makes individual actions cheaper, but it also increases the complexity of scheduling, accelerating bottlenecks in software synchronization and material delivery systems always. This coordination bottleneck alters the distribution of manufacturing value. Factories that optimize integration capture the economic surplus, while over-specialized but poorly coordinated facilities face severe capital depreciation in this scenario. To analyze this scenario, we must define the division of labor. Historically, Adam Smith established that dividing production into simple, specialized steps increases worker productivity and output significantly. This specialization increases output by saving worker time and developing narrow skills. Instead of one craftsman building a whole product, 20 specialized workers split the tasks sequentially inside the modern facility. Interestingly, this classical principle assumes a human labor pool. When fusion-era automation replaces humans with robotic arms, the cognitive and physical mechanisms of specialization change completely in practice. We begin to partition code, allocate sensors, and deploy narrow robotic mechanisms. Under this assumption, our demand for specialized machinery increases until physical transmission limits are reached always. The key distinction is that while human specialization saves learning time, machine specialization requires massive software integration. We cannot coordinate distinct machines without rising communication overhead costs within the system. For example, linking 50 specialized micro-robotic arms requires complex feedback loops and sensor networks. These digital systems consume communication bandwidth, creating significant data congestion and operational delays indeed. For instance, instead of adjusting tools manually, software must coordinate microsecond alignments across multiple nodes, substituting network bandwidth for human coordination in a clean factory environment always during production. These communication networks restrict the speed of task execution, artificially limiting throughput. Resource-poor operators find themselves overwhelmed by software complexity, creating operational friction over time under this assumption. The core mechanism of this transition begins with the cost structure of specialization. Because machines do not get tired, the marginal cost of repeating one action is zero. This shift moves the production frontier outward, creating a massive output surplus. Managers respond by substituting specialized hardware for flexible general-purpose machinery wherever physically possible today on the line. Follow the incentive structure. If hardware is cheap, companies will choose to deploy narrow, single-task machines if they save on the expensive programming required for multitask robotic systems. This substitution increases the demand for specialized connectors and local processors. As multiple assembly lines automate, they all compete for the same limited pool of interface bandwidth, raising prices. These interface constraints restrict the throughput of the factory, artificially raising unit costs. Operators find themselves dependent on proprietary software standards, creating software lock-in over time in this environment. Furthermore, the physical cost of task coordination intensifies. Using specialized machines to process different parts requires moving materials between nodes, leading to transport delays and buffer space requirements. This material handling requirement triggers layout bottlenecks and congestion, creating physical limits. Projects are delayed and the cost of factory space rises, creating a new form of scarcity. This layout scarcity limits the rate of output expansion. The abundance of electricity cannot bypass the physical geometric constraints that govern the arrangement of machinery on the floor. To evaluate this model, we must establish its boundaries. Under this assumption, the division of labor ceiling only binds if the physical layout of the factory cannot be expanded. For instance, if factory space is unlimited and cheap, layout constraints would be minimized. In this case, specialization gains persist, and the productivity ceiling does not materialize easily. Additionally, an alternative equilibrium could emerge if wireless power and data transfer advance rapidly. If engineers eliminate physical cables entirely, communication and layout constraints would be temporarily averted. However, this wireless substitution assumes that signal interference does not create its own bandwidth limitations. In practice, every technical solution introduces a new set of hardware dependencies always. We must also note the geographic limitations of supply chains. Even with autonomous factories, receiving raw inputs requires proximity to transportation hubs, shipping lanes, and primary resource mines. This regional boundary means transit hub land values will rise, offsetting manufacturing savings. In models where land is private, landlords capture the economic surplus generated by the automation technology. A validating case is found in the history of microchip fabrication. Photolithography specialization eliminated manual etching, but shifted scarcity to cleanroom dust filtration and silicon purity constraints permanently. This brings us back to our opening question of how efficiency is redefined. The answer is that software integration capacity and layout flexibility replace labor as the primary strategic assets. The consequence of this shift is a reorganization of industrial design. Factory dominance is no longer determined by labor cost, but by the elegance of the machine communication architecture. Change the assumption, change the equilibrium. If we establish a modular factory with self-reconfiguring machines, we could theoretically decouple production efficiency from specialized hardware constraints in this scenario. Under this assumption, free energy is used to power automated physical reorganizations that rebuild tools instantly. This would stabilize capital costs and prevent specialization bottlenecks over time indeed. However, achieving instant physical reconfiguration requires high mechanical complexity and faces wear limits. We cannot rebuild machines indefinitely without parts degradation, meaning maintenance costs never fall to zero. Until material science reaches that level, the specialization constraint remains binding. The practical resolution is that automation will intensify, rather than resolve, our coordination and scheduling conflicts indeed. This reality forces us to reevaluate the promise of autonomous manufacturing. The technology does not lead to costless production. It merely changes the nature of what we must manage. By recognizing this bottleneck, we can avoid the mistake of assuming robots solve all limits. True efficiency requires managing our data networks alongside our physical mechanical tools properly. The core mechanism of this transition begins with the supply curve of automated parts. Because machines run continuously, the marginal cost of executing one movement drops close to zero. This shift moves the production frontier outward, creating a massive potential surplus. Operators respond by specializing machinery to eliminate human latency wherever it is physically possible, always on the line. Follow the incentive structure. If automation is cheap, managers will choose to run highly specialized processes if they save on the expensive software debugging required for general-purpose robotic systems. The resulting interface disruptions cause high scheduling volatility in production runs. Operators cannot project delivery times, leading to reduced long-term investment in new assembly lines always in this system. Change the assumption, change the equilibrium. If we establish a modular factory with self-reconfiguring machines, we could theoretically decouple production efficiency from specialized hardware constraints in this scenario indeed. Under this assumption, free energy is used to power automated physical reorganizations that rebuild tools instantly. This would stabilize capital costs and prevent specialization bottlenecks over time in this setup. By recognizing this bottleneck, we can avoid the mistake of assuming robots solve all limits. True efficiency requires managing our data networks alongside our physical mechanical tools always. Ultimately, physical factory throughput is governed by coordination limits. Any attempt to expand specialized automation will tend to collide with the finite bandwidth of the communication networks in place. In practice, when evaluating future factory designs, we must look beyond robotic speed. We must inspect the communication architecture required to synchronize the machines, If a proposal lacks a clear strategy for resolving network latency, it is likely to face high capital costs, regardless of labor savings in this factory. We should analyze automation scenarios by testing which communication interfaces face the greatest data pressure. This helps identify the true constraints of the layout model. Another application is to invest in modular hardware research. Developing self-configuring machine interfaces is a necessary step to unlock automation value over time in these systems. Furthermore, we must compare centralized scheduling algorithms with market pricing. Distributed scheduling tend to adjust faster to material bottlenecks than quotas can in this environment. We must also maintain a clear distinction between a speculative scenario and a forecast. This analysis helps us map incentives, not predict exact outputs. By focusing on follow the incentive structure, we can better evaluate the long-term feasibility of industrial projects, avoiding the hype of costless automation systems. The critical step is to design interface standards that manage data exchange efficiently. Only then can we prevent automation from triggering coordination collapse in the factory. We must look beyond the robots and analyze the networks that coordinate their movements. The future is just incentives at scale. See you tomorrow.